Right. Okay, we're going to get started. Welcome, everyone. Good afternoon. This is Southern California Water Dialogue. We've got another exciting show today. This is Connor Everts. I'm the moderator at the beginning of the program to announce and tell you all a few ground rules. This is a webinar format for Zoom, so you won't be able to see the other participants. Sometimes we get that request, but we're going to have a good number on and a great presentation by Dr. Michael Gunson from JPL and NASA on climate change and predicting future water availability. This seems quite timely where we are right now and these varying conditions we've had even in the last week. So I am the executive director of the Southern California Water Dialogue. My co-chair is Dee Zink, who's the assistant general manager and chief of external affairs for the Metropolitan Water District. We have a list here of our Water Dialogue Steering Committee. These are the people who are pulling together the program every month, but we really rely on Kathy Caldwell, who is our Southern California Water Dialogue Coordinator. So I also want to include her, and also what we call our technical committee, including staff members of MET and others who pull this together beforehand. If you have any questions or any concerns, please use the chat and communicate with Joe and Carrillo if there's any problems you're having. So if you want to ask a question, use the question and answer feature, type in a question, and the questions will be addressed after the presentation. So hold on to that dialogue. If you have a poor connection, move closer to your wireless router and turn off any other services using bandwidth. You can also turn off your video and just have your audio if that helps. All right, the presentation today is going to be about 40 minutes, followed by the question and answer afterwards. Here's an example on Zoom on the bottom of your screen to use the question and answer. It may look a little different if you're on another device, an iPad or a phone device. Type in the question, click send. You can actually upvote by using the thumb up option, and then the question will move to the top of the list. We will consolidate some questions if they were obviously asking the same thing. Again, we do the presentation first. You won't be allowed to interrupt even if you want to, unlike when we were in person. And the dialogue will go afterwards, and then we'll have concluding remarks. With that, here's a bio for our speaker today. And I want to let Mike take it away. Thank you all very much.
Thank you, Connor. Thank you, Dee. Let me test our capabilities. Thanks for the invitation to speak. This is something that I discussed with Fred O'Callaghan and I'm happy to reprise this presentation on the role of water as a greenhouse gas. And in doing so, I'm hoping to give you all a real sense of the challenge in predicting future water availability in a changing climate. And at the heart of it is understanding perhaps a couple of things around about the complexities of water and its behavior and role in climate, and also what's driving climate change, that is what's happening with carbon. So without further ado, I'm not going to tell you what I always keep a little list of things I should talk about at the beginning of a talk, and we'll jump straight into it. So apologies first. I'm a bit of a troglodyte as far as doing animations. And in order to give a sense of the steps or components of and role of a greenhouse gas, I resorted to very basic, use a whiteboard, use my markers, take a picture, and keep developing my animation in that way. So with that, I do apologize for this. It's pretty obvious to everybody that the energy in and temperature of the Earth is completely governed by the energy we receive from the sun. That isn't very difficult. Remembering that the sun is very hot, you could represent it as being a body at mean temperature of around 5,777 Kelvin, in which most of the energy and light is in the visible region that we see and receive. That's roughly the peak of the black body radiation. If the Earth were a complete shiny ball-bearing surface, any of that light would just be reflected off and it wouldn't heat up at all. But fortunately for us, we have a body on which there is the presence of water, and that's actually kind of key. We have a real surface. So you have water, we have soil, exposed regolith, we have trees. So it doesn't simply reflect to space. Some of that is actually absorbed by the ground and heats up. A little bit of it will actually penetrate into deep water and may heat that up. But what's really more important is that whatever happens in terms of heating the surface up, some of that radiation at night, that energy, is going to be released back into space. And so really, if you can imagine, the key component of the greenhouse effect is that the energy released back to space is going to take it the form of not light as we receive from the sun, but because we're at a very cold temperature, it's going to be in the infrared. It's going to be at very long wavelengths, much further removed from the visible region. And that's just a point to remember. So my cartoon here is just a reminder that at short wavelength, on the left hand of that axis, most of the energy from the sun is we receive is in the visible region, whereas the energy we push back to space, in the absence of an atmosphere, it would be around about 260 Kelvin, which is pretty cold, and it would be much smaller amount than the energy we receive, but it would be radiated back to space. Now, it's not that simple, and we're a lot warmer than 260 Kelvin because of the presence of substances like clouds in the atmosphere, which absorb some of that radiation and that cooling radiation that should go back to space, and that keeps the atmosphere at a higher temperature. Since living in Southern California, you can get an experience, particularly in arid desert regions, where you can be very hot during the day, but by golly, it can be very cool at night as you see all that heat and energy radiate back out to deep space. But you notice in some mornings when it's been cloudy at night, it's actually warmer. There's mornings particularly in the wintertime, where it's clear at night, and you'll get frost on the ground because it's been that cold. That is just the greenhouse effect in operation. You're seeing the difference between heat being radiated straight back out to deep space versus heat being trapped in the atmosphere in the form of a greenhouse like substance, like a cloud. And that is really the greenhouse effect. Now, of course, the cloud itself, whatever substance is warmed up as that energy is radiated from the surface, re-radiates it all around. So some goes back out to space and some is retained and radiated back into the atmosphere to warm it up. During the day, and this becomes important a little later when we talk about the complexity of water in the atmosphere. Clouds, for example, can have all kinds of different properties. A cloud can be quite white and be very reflective of the sunlight we'd normally see at the surface. So that has a cooling effect. Other clouds can actually be make it feel warmer at the surface because some of that heating is absorbed by the cloud, that energy, that sunlight, and it's radiated back down towards the surface. So there's this complicated effect depending on whether the ice is made up of water droplets, which can make it appear shinier and more reflective, or made up of ice crystals, which can actually lead to a warming effect, ironically, below the cloud. It can depend on where the cloud is in the atmosphere, whether it's a low-lying marine cloud, can be very different than a mid-level cloud or very high cirrus clouds. They all have very different effects. Now, of course, when anybody mentions the greenhouse effect, we automatically think of greenhouse gases, and that's because the atmosphere has a number of gases in it which do absorb the energy being radiated back from the surface to space, and they can absorb that radiation and actually warm up the atmosphere. Water is one of those greenhouse gases, as is carbon dioxide, as is methane or nitrous oxide. There are a number of them that have the property of absorbing that energy in the infrared wavelengths and then maybe reabsorbing it, warming up and re-radiating that energy around them. That's the role of a greenhouse gas. But one of the most important things to take away is that there are other greenhouse-like substances, such as clouds. If there were no greenhouse-like substances in the air, water, clouds, or carbon dioxide, any of those gases, you can demonstrate that the Earth would be at a very cold temperature. I said about 260 Kelvin, maybe a bit warmer, but we're actually 30 degrees or more, well, let's call it 15 degrees above freezing point because of the presence of those greenhouse gases. It's essential that the Earth has those presence of water and those greenhouse gases just to create temperatures at which life can actually form and thrive. So I'm sorry, but as it's my talk, I like to take a little diversion into history at this point, because I get the sense when I've talked to people that the greenhouse effect is so new and novel in terms of scientific discovery or interest, and it really isn't. And I was very pleased to discover, I think it was through a column in the New York Times celebrating the double centenary of the birth of Eunice Newton Foote, an American woman scientist who was actually one of the first people to publish a paper in 1857 on a set of experiments she conducted where in closed bell jars, she trapped different gases and noted that carbon dioxide, for example, and water, after they'd been exposed to sunlight, stayed warmer longer than just air. And this was actually kind of a very profound insight, but maybe came to the wrong conclusions about why, because I don't think at that point there'd been a sense of the differentiation between light at visible wavelengths and light at infrared wavelengths. So I think we should be quite proud. Her father, by the way, was called Isaac Newton, and he was absolutely no relation to the other Isaac Newton, but that was just another curiosity. Anyway, Eunice Newton-Foote, almost 160, 70 years ago, started doing some very basic investigations, quite the pioneer. In 1859, the Irish physicist John Tyndall actually performed much more sophisticated experiments in his laboratory in London, whereby he actually identified the properties of gases like, and he called it carbonic acid, but we know it as carbon dioxide today, that showed that they absorbed light at these longer wavelengths in the infrared. Quite the pioneering research. People like John Tyndall and Eunice Foote, for that matter, were quite motivated by investigations to explain the ice ages and to understand why the Earth could have been that much colder for a longer period, for long periods of time. This was there was a number of scientists who'd been speculating on the origins and causes, but some of this fundamental work is, as I say, it dates more than 150 years ago. Indeed, in about 1896, Svante Augustus Arrhenius published a paper, and some of his results in that paper, which he looked at the influence of carbon dioxide on warming the atmosphere and on climate, appeared in 1896. Here's a man who, with pencil and paper, calculated the climate sensitivity to changes in carbon dioxide. 125 years later, or with the advent of very sophisticated computer technology and large-scale climate models, you'd be hard-pressed to say that we've actually been able to advance our calculations much beyond the pencil and paper of this Swedish physicist. Quite remarkable in many ways. So the greenhouse effect and the role of carbon dioxide, a role of water and other gases, has been well established for a long time. So what's the challenge? Oh, with the numbers, I've used my whiteboard, but you can find online from a number of different sources the actual numbers in terms of how much energy the Earth receives, 343 watts per square meter, and an energy balance of how it's distributed again or redistributed through the atmosphere and radiated back to space. There's a lot of interest, by the way, in understanding that radiation balance between how much we receive and how much we can measure is then radiated back to space, but I'm not going to touch on it any more than that. A little sidebar on the terrestrial planets. This is Mercury on the left, Venus, the Earth, and Mars. Interestingly, they're all little test cases on the role of the greenhouse effect. Mercury, closest to the sun, remarkably has temperatures ranging from on the order of, I think it's 100 Kelvin in the coldest parts to on its equatorial band closest to the sun to about 800 Kelvin. All of that is a tremendous dynamic range because it has practically no atmosphere, none whatsoever. However, from the ground, radar observations have detected highly reflective portions of the surface inside craters, which are fully expected to be ice trapped on the surface in cold pockets, in cold traps. So it's cold enough, even though it's that close to the sun, that you can actually find frozen ice in little pockets around craters. The Venus is an example of a super greenhouse effect. It's got a full blown atmosphere of carbon dioxide, and it is really hot. That is the greenhouse effect run almost open loop. Of course, we have the Earth, and as I was touching on, it's largely water. Thank you very much. And as a result, it's slightly warmer than it should be, given its proximity or distance from the sun. Mars, quite remarkably, has a much thinner atmosphere, but that atmosphere does contain carbon dioxide, and it does indeed, it is warmer as a result than it should be, so far from the sun. Of course, there's a lot of, we at JPL have had a lot of recent publicity from the landing of Perseverance and the 2020 lander, as NASA continues to explore whether there are indeed pockets of water, and whether there was enough conditions earlier in its life would have supported other forms of life on Mars. Anyway, just a quick tour through the terrestrial planets. They're each good little examples of greenhouse effect in one way or another. So what is challenging about water? And this is really where, given what I've said about its role as a greenhouse gas, and the fact that we're operating, we have a world where we're at almost in this realm where we have water in its liquid form, the oceans, liquid water on land. We also have water in gaseous form in the atmosphere, and of course we have ice. You can almost envision seeing all three phases of water in the famous blue marble shot from Apollo 17. It's interesting because we're right at a temperature, mean temperature, where all three phases can exist together. So you have processes in play where there's slight fluctuations as the atmosphere moves, as water circulates, where you have subtle changes in the thermodynamics, the temperature, which mean you can have water changing from any of the three phases almost continuously, in effect. So on the left-hand side here, just as a reminder, is a cartoon of of the water cycle. So you can have water evaporating from the oceans. It can condense in the atmosphere in terms of clouds. Remembering, clouds come on all kinds of scales, whether it's a nice sunny blue sky we have in Southern California today, but we've all had experiences where you can see tiny puffs of clouds. You can see they have all kinds of scales from centimeter, meter scale activity, all the way to many kilometers or many miles. And of course, it's the clouds, what's happening to them, and how they're moved in the atmosphere that leads to precipitation, whether it's in the form of snow or rain, is really important. And a small change in temperature can drive the difference between whether it falls in liquid form or it falls frozen. And these subtle changes are really at the heart of the complexity of representing what's going to happen in the water cycle in a climate model, a big numerical model that we can hope to run and understand the behavior and predict what's going to happen to water in the future. So the big questions in climate science, I think, can be, I've summarized them here. Other scientists, other hydrologists may pose them in a different way, but in my view, the future is going to be driven is, how does the water cycle change? More precipitation, increased storm intensity. Bearing in mind the last season, the Atlantic hurricane season, was one of the longest on record, and included, we went from named storms through the going through even the Greek alphabet. So it was quite a remarkable year last year. Is that the future? will it be repeated this year? Reduce snow and ice cover if the surface gets warmer. We're seeing, if you wanted a barometer or a measure of how quickly the Earth is changing, you just look for where the ice is. You look for look at the changes in sea ice extent in the Arctic. You look for the changes in surface ice in the Great Glaciers and the fact that they're changing. You look at the freeze-thaw date on the major northern rivers have all been, the frozen state duration has all been shrinking, whether it's the time they freeze to the time they thaw in the spring. How will how clouds change? As I hinted at, will we get more high clouds? Will they trap heat as a result? Or will we get more low clouds, which reflect more sunlight if they're whiter, as it were, and they have more droplets of water? This all drives water availability and represents a major challenge for climate change scientists in helping understand and predict the future. Now, I'm sure this is bringing coals to Newcastle, to use an old British phrase, but it's pretty obvious that our water availability and water resource management has typically relied on history to help manage what to expect in the present. What is changing now is because the water cycle is being influenced by the other changes occurring in the carbon cycle that drive changes in the energy cycle. So from a science point of view, we often separate out these challenging sets of processes involved in water. So I have colleagues who definitely identify themselves as hydrologists. There are people like myself who work on identifying what's going on in the carbon cycle, and there are folks trying to understand the energy balance. But it's the interaction of these cycles which makes climate prediction really, really difficult, because we're at a point where, well, I'll skip that. So what about carbon dioxide? The changes in carbon dioxide that are occurring because of the combustion of fossil fuels is leading to an increase of a greenhouse gas, which doesn't obviously have this. It has very different properties than water. Water is, we term as involved in feedbacks, because it's changing from liquid to solid state ice to vapor continuously. It's deemed, it's a response to climate change forced by the changes we see in atmospheric carbon dioxide. So in this slide here, I've got what is called the Keeling Curve, started by Charles Keeling many, many years ago. In fact, in 1958, if I recall, International Geophysical Year. A Southern Californian who spent his life in research, first at Caltech and then down at the Scripps Institute. And it's such an iconic record for climate change in this continual buildup in red, that he started the measurements on the top of Mauna Loa Observatory, trying to understand what the background concentration of CO2 is in the atmosphere. And it's a record that's been continued today by NOAA and the Scripps Institute. This record shows it's grown from below 320 parts per million, very, very tiny amounts in the atmosphere. But I can tell you that today we've breached 420. That is a huge increase over the past 70 years. And this greenhouse gas is leading to the change. It is a driver of climate change. Now, you can see in these red oscillations that some of the nuances of what we're trying to understand is, you can see that it rises in part of the year and then drops in the fall, rises in the winter, drops starting in the spring through the summer, back into the fall, and then rises again. This is colleagues of mine have used this as saying, watching the Earth breathe. Why? Well, sorry, let me go back to that. What we know, or nearly all of us know, is that what you're seeing is the effect of the northern hemisphere plants coming out of hibernation and starting to grow again. So they're absorbing carbon dioxide, and through photosynthesis, creating more glucose and cellulose matter to grow and sequester carbon out of the atmosphere. How much of that the plants can absorb is almost in the magnitude of these cycles that you can see here, but they're not the same everywhere. And understanding the role of the plants and indeed the ocean, which can absorb some of the CO2 out of the atmosphere, is really the focus of carbon cycle science today. So what are the big questions with regards to the future and what's going to drive climate change, and hence what's going to drive changes in the water cycle? Well, I'm sorry, this is a complex figure on the right here, but I'll try and step through it. The first question is, how much carbon dioxide will we, I'm very deliberately using the word we here, put in the atmosphere? If you look on in this middle figure, you can see some blue colored curves. Each of those represent socioeconomic scenarios under which we either, the lowest one is where we stop consuming a lot of fossil fuels, to the red one, which appears to be the most aggressive of all those curves, where we continue business as usual. In our lifetimes, in my lifetime, in up to 2020, we're still on that red curve. We're still globally dependent on fossil fuels for energy. So we've been on a track to continue putting carbon dioxide into the air. And the best calculations show that if we do, over these extensive timeframes, you could see a significant warming, increase in the mean global temperature. Now, how that would affect the water cycle is much, much harder to predict. But our basic calculations, which use some of the basic math that Arrhenius and Tyndall established, show us that we're going to get into a warmer world by several degrees. But one of the things that helps remediate that or mitigate that is, how much can the oceans and the biosphere absorb? It's a big question, because since the Industrial Revolution, only half of the carbon dioxide we have put into the atmosphere from burning fossil fuels has remained there, roughly. Half of it has been absorbed by plants or dissolved into the ocean. And that's kind of an amazing thing. But how much can the biosphere, plants, and how much can the ocean continue to absorb and keep us off one of these curves, warming curves? So I'm going to, I just want to, yeah, maybe I should just spend a moment here. And this is another, sorry, complicated plot that shows from roughly the Industrial Revolution on the left in time through to the modern period, how much carbon dioxide, called a flux, how much we've put into the atmosphere and how much has been taken out. So in gray at the top is an estimate of how much fossil fuel and industrial activities have put into the atmosphere. Below, and there's a small amount in gray below the gray box, below the gray line is a small beige line, which is to do with how much change has been caused, how much carbon dioxide has gone in from deforestation and land use change, as it's called. Below are what we see as the residual from that. How much in dark blue has the ocean been able to absorb? How much in light blue remains in the atmosphere compared to how much we think has been picked up in green by the land? As it's remarkable that as the amount we've put into the atmosphere year by year has increased, you can see the amount that's been taken up by the land and ocean, it's not quite as changed as quickly, but it's still taking a good fraction of that carbon dioxide out of the atmosphere. The residual the residual obviously remains in the atmosphere, and that's why concentrations are increasing. So what assumptions can we make about what we're going to put in the atmosphere is a big one on predicting climate change. What's happening on regional scales? That's probably not for this talk, but an interesting set of questions come there. And how will they change with time? Will the ocean sink change? Will the land sink change? They're first order questions in the carbon cycle. So my job on a daily basis has been involved with the Orbiting Carbon Observatory, which was launched now more than 6 years ago. We come on the 7th year anniversary coming up pretty soon. If I've got my basic, or is it 8th year anniversary? Get that right. I was there for the launch out of Vandenberg Air Force Base, and I remember it very clearly, getting dropped off at 2:45 in the morning in the mist, hearing the rumble and not seeing a damn thing. This is the only way I saw it. I was to get onto NASA TV news. I took it in the neck from the family for dragging them out to see nothing for the remainder of the evening and the rest of the week. Since then, we have been we have made measurements of carbon dioxide around the world, its distribution in the atmosphere. Unless anybody thought that the distribution of carbon dioxide was kind of even and constant everywhere, it's far from it. The distribution reflects where carbon dioxide is emitted into the atmosphere, i.e. largely in the northern hemisphere in the well-developed countries, and where it's absorbed out of the atmosphere. So that's what this color range here from 380 to 415. This is a highly smooth map, of course, but it gives you a sense of the measurement challenge for us. And then once having these measurements, how other colleagues and scientists are trying to understand what's happening at the surface to understand where that carbon dioxide is going. One of the examples of things that is changing right now, and it was reinforced by a paper that appeared literally last month, is there was an expectation maybe 20 years ago that the great Amazon forest, the Central African region with its great rainforests, and Southeast Asia were major biosphere components, were there to absorb a lot of the carbon dioxide out of the atmosphere as they grew and continued developing as plants. But what we've found since then, and I'm not going to spend a lot of time on this, I assure you, is that even backed up by recent results, that it's no longer appears true. The tropics have changed. What we're seeing now from our best observations and calculations is that the tropical regions are either neutral as far as how much carbon they take out of the atmosphere or how much they put back in from either fires in Indonesia, for example, or from just the death or changes in forests in Africa, in the Sahel, or to the fact that there seems to be not only deforestation in the Amazon region, but plants are slowing down in their growth rate. So the tropics do no longer appear to have a role that we assume they have of being a major set of kind of lungs of the Earth. I won't dwell on Los Angeles, just that we can actually measure something about human activity. So here are the takeaways. First, just think of the greenhouse effect. Think of water, clouds, and particularly aerosols. Don't think just about greenhouse gases. And it's the changes in clouds and aerosols and the feedbacks they provide in cooling or warming the Earth and how they affect precipitation and hence water availability. That's one of the great challenges in climate change. What forces those changes, and some of the big questions which I'm kind of partially interested in, is how much will we see a change in atmospheric carbon dioxide? How much will we put in there? And how much more can the oceans absorb and the land? The exact answer is intimately related to what we see or what we can predict in changes in the water cycle. That makes predicting in a changing climate what's going to happen in water availability really difficult to be accurate or to be confident in what we can expect, even on a 5-10 year time frame. And with that, I'd like to thank you and for your attention.
Well, thank you very much, Dr. Gunson. This was a very heady presentation, at least for me, and I was trying to follow all the way through, but we've got some very smart people in our audience today who have some questions. We're going to go ahead and start out with a Q&A, and please, just a reminder to everyone, if you would type your questions into the Q&A section you'll find at the bottom of your screen. Just hover over that and it will allow you to type questions in, and then we will field questions with Dr. Gunson. And I'm going to start out with something that may be a little out of your world in terms of your familiarity, but we have a question from Diane Wallace, who says she's a native of LA. When she was a kid, she recalled announcements in the news that clouds were being seeded. We weren't aware of what was being used to seed the clouds, but the purpose was to increase rain. Is this something that still can be done, provided it is environmentally safe? So I don't know how familiar you are with cloud seeding. It is actually still done, I'm aware, but is this something that you can talk a little bit about, Dr. Gunson?
I'm only aware of the fact that as a yes, that is still being practiced, and as I understand it, it's been tried on a much larger scale in China, but it's not. We don't I don't think we fully understand the real efficacy, or B, the consequences fully of trying to seed clouds for precipitation, trying to manage the hydrology cycle or manage precipitation is, it would be fantastic if we could find the control, as it were, the dial that allowed us to manage when precipitation occurred and increase it particularly in dry areas. But I'm not really aware of any of the other details, except that it wasn't it iodine or iodide seeding that was tried. I don't think it's super reliable, but I know it's been tried extensively in other countries, particularly China.
Thank you, Dr. Gunson. And anybody that is typing in Q&A, if I think we have representatives from LADWP or others, you may have the ability to respond to that question in writing, and we'll call that back up. It does raise this question, though, about are there other things that we can do to manage the clouds? And I don't know if that's anything that NASA and JPL are working on to give us some hints, or how we can better forecast, because that's a big part of what we're trying to do, is forecasting water availability, and in particular long range, so that we can determine what types of infrastructure we need in order to adapt to climate change.
I will say that over this is a change and a new emphasis that's occurred in the past 5 years, maybe started 10 years ago, but certainly past 5 years, is there's a great deal of interest in improving. So we're very used to the idea of being able to use the weather forecast and giving us something on the 10-day time scale. We just see that on your smartphone. Climate change modeling, we felt we could. I think research had got to the point where we're confident in saying, yes, we can do mean level predictions or projections of what might happen on decadal scales out to a century. But you're quite right. The gap in between doing seasonal forecasting and interannual variability or interannual forecasting is a new point of emphasis in a lot of research. There's an initiative with my colleagues at Caltech on trying to understand how to improve predictions even down to a decade scale. The colleague Dwayne Wallacer JPL with people like Marty Ralph down at Scripps and elsewhere have put a lot of research energy into understanding season to season forecasting, particularly the role of atmospheric rivers in being a key precipitation we can see in the throughout the year. So we're at this is absolutely the frontier of research right now, is establishing more confidence and the ability to forecast at the seasonal to interannual scale. Something that I think, you don't have to live in Southern California for very long to realize how critical it is to understanding whether we're going to have enough water on that kind of timescale.
And to be able to manage our reservoirs. Let me we have a few more questions that have popped in now. One is from one of our directors at Metropolitan, Russ Lefebvre. He is asking, what is the sensor on the OCO-2? Can you explain that?
Yeah, in actual, of course, a lovely question. So we actually use a sensor which looks at reflected sunlight. So as the sunlight passes all the way through the atmosphere and is reflected off the ground back to space, the sensor can looks at that sunlight at different wavelengths, where the sunlight is absorbed by carbon dioxide and oxygen. And we, in effect, we can then measure the amount of carbon dioxide in the atmosphere that the sunlight has passed through against the amount of oxygen, and we can then determine the concentration of carbon dioxide in the atmosphere from that ratio between the amount of oxygen and the amount of carbon dioxide. The interest is how much of how does that vary as you move across the ground and in time, because the differences between one spot and another in time and space is how much change has occurred at the surface, how much has been either released into the atmosphere or how much has been taken out. Hope that was the answer.
Thank you. Well, I'm sure he'll weigh in again if it wasn't. I have a couple of questions that are getting plussed up and coming to the top. So this next one is from Adrian Hightower. And he is asking, the global map shows extreme variance in CO2 levels at the North Pole versus the equator or South Pole. Could you discuss the mechanism behind these variances?
Certainly. So the first major component is that most people live in the Northern Hemisphere, and that's where most of the fossil fuels are consumed and burnt. So if you imagine the largest input of carbon dioxide to the atmosphere occurs in the north, much more than the south. So then the other key thing to bear in mind is that the mixing of air, you probably all used to the idea that air circulates around the world east to west. However, let's call it west to east. North to south, it doesn't mix very quickly. So you automatically see a difference. One, because most of it goes in the north and most of it's less in the south. It takes a long while for that difference to mix out. So you always see a higher level in the north compared to the south. What's further complicating this is that storm systems tend to move air from the equator out to the north. So air rich in carbon dioxide tends to, you see much bigger cycles and fluctuations in carbon dioxide at Barrow on the north slope in Alaska than you would at Mauna Loa. And that's because the storm systems are taking CO2 rich air and it's kind of accumulating a little bit before it's mixed back out at the north. So you see a very high contrast between the concentration of carbon dioxide in the northern polar region compared to the south, primarily because of the difference in where carbon dioxide is put into the atmosphere, i.e. north versus south. And secondly, just because of the way the atmospheric circulation patterns work. D, you're on mute.
It had a big band across my screen that said that, and it took you to tell me that to make sure I got off mute. I was saying I had a similar question because of your graphic, so that was helpful to hear. The next question is from Raghu, and I apologize if I don't get this name right, but it's Suribatiya. And the comment first is great presentation. Regarding impact on the water cycle, do we see large-scale changes in vegetation and the general response of biota in terms of adapting to higher CO2 in the atmosphere, and whether they are increasing the water requirements?
Great question. Great question. So one hypothesis has been the idea that under increased carbon dioxide levels in the atmosphere, certain plants would thrive, and you'd see an increase in photosynthetic capacity of plants to grow, and primary productivity is one of the phrases that's used. So yes, you would see a greening. That has been some measurements would indicate that that's happening, that there is an increased capacity of plants to take up carbon dioxide in mid-latitudes and in northern latitudes. Further, but this is controlled by both temperature and water availability. So in the case of temperature, for example, as an example, because we're seeing a lengthening growing season, i.e. it's warmer longer, you actually see plants start their budding, and I know that plant biologists have a better phrase for that, but when they start growth and budding, it's happening earlier because of the warmer temperatures, and that's encouraging growth. But in other areas, for example, in the Amazon, where we're seeing a great change in water availability and increase in temperatures, we're actually seeing plant primary productivity is probably being suppressed. So you're actually seeing one of the other consequences of climate change is, as I tried to emphasize, the tropics, that band of green that cuts across South America, Africa, and Asia. There seems to be fundamental changes going on there. Not only are we seeing drier seasons, so you have, I think most of us recall that there were those massive peat fires in Southeast Asia that's mobilizing carbon stored in peat below ground, like a fossil fuel. It's being taken out below ground and put back in the air. So we're seeing fundamental changes in plants driven by, yes, temperatures in some areas are warming, so it's improving growing conditions. Temperatures are going to a point where they're so hot, they're killing plants. And all of it, plant growth, is critically coupled to changes in the water cycle. So when you see extended droughts occurring, it's changing the role plants can play in taking up carbon dioxide. So all of those are very complicated in terms of their regional, spatial behavior and temporal behavior, and are very difficult to capture in models to predict how what's going to happen in the future.
We are seeing this early plant uptake in our own watersheds that feed Southern California water supplies, and we'll talk a little bit about that at our meeting next month. But let me move on to the next question. We have a question from Dawn Taffler, and her question is that she recently watched the documentary Kiss the Ground, and she put a little link in here for those of you that are looking at the Q&A. And it looks at the ways in which the Earth's soil may be the key to combating climate change and preserving the planet. She's asking if NASA is doing research on soil management as a carbon sink, and perhaps the nexus with water use as part of better soil management.
So just to say, NASA's purview on research is wholly driven by remote sensing, i.e. what we can see from space. That's the domain that NASA typically funds research. I do know that there's an awful lot of interest in carbon storage in soils and agricultural practices. To what extent the amount of carbon that you can actually infuse and store below ground in soils is something I haven't seen the basic calculations. My only caution on this is you can, it will be a component. I'm not going to say it is not a component, but the basic calculations on the magnitude of how much carbon we have to see sequestered and removed from the atmosphere is simply enormous. I'm doing we're talking gigatons, so we're talking billions of tons of carbon that have to be managed. It is a daunting prospect, but all practices, agricultural, even, it's equally viable, in my humble opinion, along with practices about transportation, how much you can electrify your transportation system, for example, etc.
Yeah, we need to have hope. So
Yes, we do.
Appreciate that opportunity to do everything. We've got a question now from Blake Caldwell. He's asking, as temperatures increase, will the greenhouse impact from water increase temperatures proportionately or exponentially? And does that increase have significance compared to CO2's role on temperature?
So it's a great question. So really, we have carbon dioxide gets in the atmosphere, and what I tried to convey is that it doesn't leave the atmosphere until it's taken out by a plant or it absorbed in the ocean. That's the only way it goes. So it's kind of a forcing of change of the greenhouse effect. Water is this very complicated, in some forms, the water cycle, in certain levels of clouds, you can actually get a cooling effect. So even as carbon dioxide and other greenhouse gases outside of water are forcing the mean equilibrium temperature up, the response from water is much more complicated. Whether it's going to condense into clouds at some level, whether we're going to see an intensification of evaporation and precipitation, because what could happen is you're putting all the energy into accelerating the water cycle between evaporation, cloud formation, and precipitation. I remember many years ago, a colleague, former chief scientist at JPL, doing the calculation that's an average water cycles at about 11 days. If that shrinks a little bit to say 10 days or 9 days, what you've done is you've forced a lot more water up and you're getting a lot more precipitation. It may be incredibly inconvenient precipitation, but that could be the response of the water cycle. So it's not that it's a very nonlinear process. That's true. Whether it's an exponential increase, I don't think so, because it's all tied up in projections of what happens to the water in the atmosphere, whether it's clouds, whether it's low clouds, and where it precipitates. I'll just say this while it comes to my mind. If you look at any international report on climate change and you look at what a model would say about cloud cover, they show the starkest contrast of responses. Some models show massive changes in increasing cloud cover. Some show a decrease in cloud cover. It is that difficult to predict. Complicated answer.
Thank you.
Sorry about that.
I'm going to switch gears a little bit. We have a question that's been endorsed related to wildfires. This comes from Christy Taylor, and she's asking, as wildfires become more frequent and more intense, especially here in California, is there a mechanism to include the GHG emissions from the wildfires in predictive models? She goes on to say, I imagine it would be difficult to add because it's hard to predict how many fires will happen, where they will occur, and how large they will be. Also, the impacts to watersheds from wildfire damage will impact the water cycle, which impacts climate. She says she's just curious what your thoughts are related to wildfires, climate, and water availability.
Great question and very great observation, actually. We've had, there's a lot of current research work going on to understand the contribution of wildfires to the carbon budget, how much is getting into the atmosphere. There's a great deal of, obviously, there's a great deal of concern about not just here in wildfires in California, but you know, clearing fires in the Amazon, for example. There's evidence now that as you do land clearance in the Amazon, for example, it's affecting the local climate in a major way. So because plants in the Amazon affect the hydrologic cycle, it's plants who initiate the wet season. When they start growing, part of it is sucking water out of the ground in evapotranspiration and putting water back in the atmosphere. And that humidification leads to the intensification of the water cycle down there and the wet season. In California, another example of the role of the biosphere in wildfires, will they recover? Because if we see a drought and we see a change in pattern of water availability, it's not clear that that carbon stock, so you've got carbon stocked up in trees, whether we'll regrow that, whether there'll be an opportunity to do that, and how resilient they will be. But they are an important factor. There's discussion about whether they should be, how to account for them in national stock takes of carbon. Because if you see carbon dioxide going up from traditional fossil fuel consumption, and there's also a component from wildfires, how should they be accounted for if you're trying to manage how much carbon dioxide is in the atmosphere?
So it sounds like it's a discussion, but it's not resolved yet in terms of being able to track and calculate. Okay, thank you.
We can try. There is some attempts to, but I think the uncertainty, the error on how much we can say has been moved is larger than is useful at the moment.
Very good. Okay. Our next question comes from Shelley Posner, and she says, sometimes we have rain clouds overhead and it doesn't rain. How is this related to what we're doing to the land, artificial surfaces versus plantings?
I'm not sure the answer to that. I'm not sure that the coupling between what's happening on the land and the thermodynamics, the temperature controls that go on in a cloud that lead to precipitation are that close. So I'm not sure that there is a control mechanism there. There are places where if you have, go back to the example of the Amazon I was talking about, there are places where you have very low clouds perhaps, and if you have an intensification of water being put into that cloud, you get more likely to have precipitation. But I'm not sure that what we're doing in terms of land use change and land cover change influence or suppresses precipitation in clouds at, say, the mid heights or that kind of level. I can't quite envisage a mechanism that would connect the two.
Well, this is sort of a related question, and it comes from Pierce Swan, and he says, large-scale agriculture appears to have increased CO2 levels. So what are the causes and how can we change? There's one of your land uses.
Ooh, that's a good question, Pierre. So there's two things going on there. Well, there's several things. First off, you've got land use change. So you're clearing a natural system out of the way to devote it to crops or maybe livestock. And usually that means you've reduced the ability of that portion of the land to absorb the plants there are no longer taking out carbon dioxide out of the atmosphere when they're growing. The next is you actually have, particularly livestock. I had this argument with my beloved who loves her steak, that a steak has one of the highest carbon footprints of any form of food that we consume. And that's because you have to put an enormous amount of energy into the system to create that steak. And in fact, that's true of any crop. You're going to get on the tractor, you've got to harvest it, put it, and you've got to bring it to market, all of which has a big carbon footprint. Then there's what happens afterwards, you know, in other areas of the world, and it's significant in, for example, practice in Africa. You have stubble burning, and you have clearing that puts, you know, you've just sequestered carbon into the plant, but the leftover plant's going to get burned. You're going to put that carbon back, and it leads to big signals in carbon dioxide that we can actually see from my project, for example, from OCO2. So I think it's land use change has a big important impact when we devote land from its natural role to agriculture. There's a big impact from the intensity, energy intensity, how much fuel you'll burn to actually raise that crop or livestock. And then there's sometimes there's an after signal of how you clear the land. Going back to an earlier question, we're not plowing that corn stubble, that crop stubble back into the ground as carbon sequestration. Anyway.
I'm really excited that we continue to have questions. This is obviously a very stimulating conversation. So, and I'm going to stay on the kind of the land use farming related topics for the next couple of questions. This one is from Carlos Moran, and he asks, are there any indicators that point to the optimal geographic regions that can be targeted and influenced by microclimate level interventions, such as planting trees and soil management? More questions for Hope.
So, well outside my personal field of research or what papers that I normally read, I've only read some very high-level articles on this, but the answer is yes. There are regions where plants do play a major role in controlling the microclimate. You can see the adverse effects of removing established ecosystems, forests, woods, all kinds of plants from a certain area, because it affects the water cycle. Those plants are growing, absorbing, pulling water from the ground and cycling it back into the air to make it humid, evapotranspiration. So the answer is almost certainly yes, but what I don't know is whether you can initiate and recover an ecosystem, a microclimate, without a huge investment of effort in bringing water back to the location, what that location would have to look like, or how long you would have to do that for. You know, I don't know whether those recovery and repair activities, as it were, in ecosystems are easy. It might be easier in heavily watered areas, in marshlands, for example. That is definitely an area where you can see recovery if you take the human influence out of the way and allow natural systems to recover in them. Whether we can expect to do that once we've cleared whole forests in certain areas on a larger scale, I don't know.
Let me ask one last question on the related to CO2 fertilization. The question is, what is your opinion on the role and importance of CO2 fertilization? And then we're going to switch to some other related topics.
So CO2 fertilization is clearly a factor in how the spurts of growth in areas of North America, i.e. the United States and Canada, in certain forest regions. But it's difficult to disentangle CO2 fertilization from the other factors of temperature change and water availability. They can be quite confounding in the interpretation of whether the tree is now bigger and greener than it would have been under other circumstances, because there are these other controls out there which are affecting whether that tree is bigger and greener, whether it's been warmer and you've got a longer growing season, whether it's had enough water, etc. So it's not there's no basis for believing it's not happening, but quantifying that effect of CO2 fertilization in isolation in the natural system of these other factors is quite a bit harder.
All right, thank you for that. I'm going to switch gears now. We have some questions that deal a little bit more with oceans, and so wanted to ask a question about sea level rise. There is I'm sorry, I skipped over one, so I apologize. Let me go back one just to talk about. Cynthia Jackson has a question. How will changes in the ocean resulting from the desal process impact its ability to function as a CO2 sink? So this is getting into desal, but I would ask that before you talk about that, can you share if there are any impacts to the ocean right now from it serving as a sink for CO2, and then talk a little bit about desal?
So there are a number of changes occurring in the oceans which are concerning. So before we got into a period where we were really fundamentally changing the composition of the air by putting so much CO2 in it, there was an underlying overall circulation pattern, a component of which was, for example, the Gulf Stream. There's the underlying movement of water around the world's oceans was moderately stable, let's say, even though there were the issues of the El Nino, between El Nino conditions and La Nina. Those oscillations were occurring under a certain regularity and cadence. Now, in a warming world, a lot of that heat is getting put into the ocean, and it's fundamentally a warming ocean is changing those circulation patterns. And a concern has been, if you have a change in the circulation pattern and changes in regions, particularly where we think cooler waters can absorb carbon dioxide out of the atmosphere, whether that role the ocean plays in being able to absorb carbon dioxide can be sustained, or whether there's a tipping point where you get a change in the overarching circulation patterns and a warming of the ocean to the point where it just does not play a strong role in absorbing CO2 out of the atmosphere. That's a physical process. It's one of those wondrous things. The ocean is a physical process of absorption of CO2, regulated by, maybe buffered underneath by biological activity, whereas the absorption of CO2 on land is a biological process very much regulated by physical conditions, temperature and water. So back to the ocean. So it's difficult. And of course, CO2 in the ocean then turns to changes in acidity, which has its obvious impact on the biosphere and biota in the ocean. And so it's a complex set of relationships, but the ocean is changing too. It's warming. And in that warming, we're also seeing there's a possibility of large-scale changes in the overall circulation patterns. The Gulf Stream is just to say, and then you have the North Atlantic with water melting off Greenland, for example. So you have fresh, cold water merging into, coming in and interacting with warm saline water in the Gulf Stream. That interaction is a real concern for what it means in terms of weather patterns in Europe, for example. Anyway, I'm rambling now, sorry.
No, you're not rambling, but there was a question about the desal process. I'm not sure if you're familiar with desalination.
Yeah,
thank you.
Well, so there's a local effect, obviously, in that it depends what you do with the saline product. It's a much more complicated environmental impact assessment than I think I can speak to, quite frankly. It is going to have there are regions where you can go and do the case studies of the impact, like around the Arabian Peninsula, where the oil-rich countries have built many desal plants, and you can see what's happened in the Persian Gulf and then the Red Sea, for that matter. It's had quite an impact on the marine life and environment there. But I think it's a case by case. You'd have to look at how the overall management and desalination process is handled to understand what its likely environmental impacts would be.
Thank you. And I'm going to go on to now Craig's question. Craig Cadwallader, he has a question about how much of sea level rise is attributed to the increase in temperatures of the ocean versus the melting of existing ice, glaciers, ice caps, etc.
Very good question. Very good question. So it's been a while since I looked at the absolute numbers, but the historically, pre about 1990 maybe, a lot of sea level rise in the century can be attributed to thermal expansion of the upper layer of the ocean. That's all thermal. That was the first. We've had about 8 inches. Walking around number, I'd have to go look at the exact numbers of sea level rise. So historically, the bulk of sea level rise to date is probably thermal expansion. However, in the past 10, 20 years, on an annual basis, more than half is now due to freshwater input from melting of land glaciers. So we're in a regime now where we're seeing the impact of influx of freshwater melt from Antarctica and Greenland, the two big sources. And of course, there's lots of pretty scary numbers thrown around with respect to what could potentially happen. But it's happening. There's absolutely no doubt we're seeing a deglaciation of in Greenland and other regions and Antarctica. And it's accounting for, I don't know, it's about the number is only tiny. It's like 3.5 millimeters total sea level rise per year, year in, year out. And a good 2 millimeters of that, I think now, is probably accounted for by freshwater influx from glacial melt.
Significant. Thank you. Okay, I'm going to move on to another question that we have. This one is from Pierre Swan. He asks, if temperatures increase, will evaporation increase and create more clouds? And will this increase the reflection of the direct sunlight and serve to cool?
That is a great question and is at the heart of a challenge of understanding what's going to happen in the future. A warmer world would lead to the atmosphere's ability to bear an increased burden of water, i.e. more, you could evaporate more from the ocean. What happens then, and at what height in the atmosphere, and how those clouds evolve is a huge question. Do they lead to larger regional cooling effects because you've got a bunch of highly reflective white reflecting clouds, or do you get really high clouds which contain ice and actually turn into a bit of a warming effect because you don't get as much cooling at night? So those feedbacks from what's happening with water are at the heart of understanding what a future world will look like. It's very difficult to predict. It's not that and the challenge is understanding a lot of, not just, you might think of a climate model like it's on a very coarse scale. There might be, this model might run with cells, as it were, covering kilometers. You're asking what's happening in the water cycle, what's happening on the molecular scale, and understanding what's happening in the rate of formation of ice crystals versus them melting and suddenly turning into a water droplet. Those kind of microphysical processes are at the heart of the challenge of scaling that understanding at the microphysical scale up to a climate model scale where you're representing things over a kilometer or more. And the atmosphere is a bit of a bear because it has this nasty habit of actually having processes which are on very tiny scales. How do you capture a tornado in a weather model? Or how do you capture a sudden squall of water? That's a fundamental aspect of the work that's to go in getting to really useful, reliable, seasonal, as well as decadal scale, anything in that range for weather for prediction.
Thank you. I'm going to ask one last question, and then so that we can close out, turn over this program to my co-chair, Connor Everett, and ask that you sort of summarize where you're heading with the science and what we should be on the lookout for. But this last question is from Andrea Delapa, and she asks, in your opinion, did we reach the point in which other less considered in the past greenhouse gases rather than CO2, such as methane and nitrous oxide, should be our main focus for regulations that contribute to their reductions? Are we there? Are we there yet?
Well, I'm going to, if I may, it's a great question. I'm going to turn it in a slightly, I'm going to turn it in a slightly different direction. The major greenhouse warming over long term is carbon dioxide, without doubt. Changes to carbon dioxide will have the most profound effect. It's because it's at the right amount in the atmosphere, and the changes to that amount at the right level. So it will be the dominant greenhouse gas we should be concerned about. However, even though it's smaller in concentration, methane on a short scale is well worth paying a lot of attention to and mitigating or regulating its release into the atmosphere. Even though it's 1,000 times less in concentration, probably more, it's probably 10,000 times less. It's per molecule, methane is a much more active greenhouse gas, much more capable of absorbing infrared radiation. So, but over the long arc, it's removed from the atmosphere because it's oxidized, it's turning to carbon dioxide. But if you wanted a local short-term action which would help, then what you would do, and what we're actively working, there's active interest in California in doing this, is you identify the release leak, actually is the best word, leak of methane to the atmosphere, and you shut it off. And this occurs in both farming and in the oil and gas exploration world. And we've had several demonstrations of how you can map out where these plumes of methane occur, identify what the responsible component is or agency is, and you can actually mitigate that. You can actually go and close off that leak, as it were. So yes, you kind of can do something. The key gases, long term, it's CO2. It will always be the most important greenhouse gas, human-made greenhouse gas. But in the near term, there's a lot you can do about methane, and you can actually save yourself a bit of warming by going and identify where those leaks are occurring in the system, whether it's agricultural, oil exploration.
Thank you very much, Dr. Gunson. This has been really informative. Connor, can you come back? Thank you. And I didn't know if there was any summary comments, but I will sign off now. Appreciate it.
Thank you, Dee. Great job handling the questions and answers. Michael, I want to thank you. At this point, normally there would be applause, but just from the reaction from the number of questions and the interest, this has been an excellent dialogue, and I really found your presentation both fascinating and enjoy the historical perspective as well. So everyone knows, we record the presentation, and we post it as well on our Southern California Water Dialogue website, and that should come up in a second. If it doesn't, I'll actually read it out. There you go. It's at the bottom of the page. It lists that, and it mentions that our next water dialogue will be on May 26th. That will be the fourth Wednesday. We'll continue in Zoom at this point. Our current working title is "The Great Colorado River Drought Worsens, Shortages Are Around the Corner and Larger Cutbacks Loom." We don't try to make these presentations depressing. We try to bring in some solutions and answers as well. But again, I want to thank our technical team and the Met support. And I want to thank all of you that participated today, but mostly Michael Gunson for his presentation. Thank you all very much. And we'll see you next month.
Thank you, everybody. Thank you very much.